Heapify. The Heapify operation helps in maintaining the heap property of a heap whenever there is a violation of this heap property at the root node. So keep in mind that Heapify is useful only when the violation happens at root node. So consider this is a heap. We have a heap like this. Let us have one more level. So we'll draw one more level for this heap. And consider that at the root node you have a violation of heap property. Then can you directly apply Heapify and get the whole heap back? No, you cannot, because there is one more condition that is to be satisfied for you to apply Heapify, and this condition is that the left subtree as well as the right subtree of the root node should already be satisfying heap property. So your complete left subtree and the complete right subtree, this should already be heaps. Under this condition, if there is a violation at root, you can apply Heapify on the root and you'll get a new heap. The complete tree will be converted into a heap. So keep in mind that if you have a violation at say at this node, in this case, if you simply apply Heapify here, you won't get the complete heap back. That is, the complete tree won't be converted into a heap. Instead, if you have a violation on this node and you are aware that the left subtree as well as right subtree of this node are already heaps, then applying Heapify at this node will make this subtree as a heap. So in short, whichever tree or subtree you want to make a heap, the issue should be at the root of that tree or root of that subtree. And the left subtree as well as the right subtree of that particular root should already be heaps. So under this condition, you can apply Heapify and convert it into a heap. So what we'll do, we'll try to understand what are the steps to be followed in order to apply this Heapify operation. So consider your root is at index I. So I'm using I instead of root because this can either be the root of the whole tree, or if you are only heapifying one particular subtree, then I could be the root of that subtree. Okay. So if I is the root, how will you find the left child and right child? Your left child, so this we discussed in the previous lecture that in the array representation, left child of any particular node can be found as 2i plus 1. So 2i plus 1 will give you the left child. Similarly, 2i plus 2 will give you the right child. So this is in the array representation of heap. If you have any particular node at index I, then the left child of that node will be present at index 2i plus 1 and the right child will be present at index 2i plus 2. So with heap, for these operations, we want direct access to left and right children as well as sometimes to the parent. So this is why we'll always use array representation for heap. Okay. So if you know the node, its left child and the right child, what are you going to do? What step are you going to do in this particular iteration of Heapify? What you're going to do is, you'll take I, its left child and its right child. You'll compare all these three. You'll see whichever is the largest element. So keep in mind that we are doing max Heapify. So if you want to do min Heapify, just do opposite of whatever we are doing. That is, wherever we are looking for the largest, you have to see for the smallest. Other than that, the whole algorithm will remain the same. So we'll be illustrating max Heapify here. If you want to do min Heapify, just keep in mind that wherever we are taking largest, you have to take the smallest. Okay. So this is the max Heapify algorithm. You'll check I, left child and right child. And if it so happens that I is the largest, whatever is at the node I, that is the root, is the largest, then you can say it is already a heap and you can conclude it there. Because you know left child is already a heap, right child is already a heap, and the value at I is larger than left and right, which means it is already a heap. So you don't have to do anything more. But if there is a violation, that is, if left child or right child is larger than I, in that case, you will swap the value at I with whichever is the largest. So if left child is the largest, what will you do? You will just swap the value at I with the value at left child. Once you complete swapping, you will apply max Heapify algorithm on the left child. So this is how you will propagate this algorithm forward and complete the whole heap. So what we'll do, we'll take an example and understand. So it will be easier to understand from an example how exactly this Heapify works. And one thing that we'll do is throughout this series, we'll be using the same tree for explaining Heapify because it will be easier for you to relate with whatever we used in the previous lectures. So we'll take the same tree. Tree is 80. Then we had 74, 32. As children of 74, 63, 50. Here 15 and 21. So as of now, this is a heap. This is a max heap. Okay, this is a max heap. What am I going to do? I'm going to keep a violation of heap property at the root. So I'm going to change the value of 80 to something like 10. So now the max heap property is violated at the root. So first thing, I have to check whether the conditions are satisfied in order to apply Heapify. First condition is that violation should be at the root. Yes, the violation is at the root. Second condition is that the left subtree and the right subtree should already be heaps. So let us check the left subtree. 74 is larger than 63 and 50, which means this node is already satisfying heap property. What about 63? This is a leaf. Any leaf by default satisfies heap property. 50 is also a leaf. So the left subtree is already following heap property. What about the right subtree? 32 is larger than 15, larger than 21. So again, right subtree is also following heap property. So you understood that in this particular case, both the left subtree and the right subtree are following heap property, and there is a violation at the root node, which means this is the right candidate to apply Heapify algorithm. So what will you do in Heapify algorithm? You will check the value of root node, which is 10. You will compare with left child, which is 24, and the 74, and the right child, which is 32. What do you have to do? You have to see which is the largest. Which is the largest among these three? 74 is the largest. What will you do? You have to swap the value of root with 74. So if the right child was largest, you would have swapped with the right child. Here 74 is largest. So you will swap 10 and 74. 10 will come here. 74 will come here. So at this point, you transfer that violation to here. So now root is following the heap property, but the violation is presently here. The next thing is that you have to apply Heapify on this subtree. What you're doing is, from initially you applied on the whole tree, then you transferred it onto a smaller subtree. Then you have to apply on this subtree. Again, you will be having to apply on another subtree. So this is how Heapify will go forward. So what do you have to do now? On this subtree, you again have to apply Heapify. So when you apply on it, you will check 10 with its left child, which is 63, and the right child, which is 50. Is 10 the largest? 10 is not the largest. So you will see whichever is the largest. So 63 is the largest among these three, which means you have to swap 10 with 63. So how will you swap it? You will swap 10 with 63. So 63 will come here. At this point, you know 10 has already reached the leaf, and any leaf by default follows heap property. So you no more have to call Heapify. So this algorithm has the base case. Base case, there are two conditions. One is, if you reach the leaf node, then you can stop. Whenever you reach the leaf, it is done because leaf by default follows heap property. Second thing is, whenever you are at some particular node and you are greater than the left and right children. If instead of 10, if this was, let us say 70, then if 70 was here and you had 63 here, at this point itself, 70 is larger than 63 and 50. So whenever the heap property gets satisfied, you can terminate your Heapify algorithm and say that the complete heap is now heapified. So these two are the base conditions. One is it should reach leaf, or it should reach any particular node at which heap property is already followed. Then you can stop it there. So this is what is the Heapify algorithm. What we'll do now is, we'll write the pseudocode, and then we'll analyze time complexity and space complexity of this algorithm. Okay. So let us first write the pseudocode. So for writing the pseudocode, the only requirement is you should have the logic clear in your mind. So what is the logic required here? First thing is you have to identify the node on which you have to apply. So we'll call it as I, the root node on which you have to apply. What will you do then? You will identify the left child 2i plus 1 and the right child which is 2i plus 2. After identification, you will check which among these three is the largest. Whichever is the largest, you have to swap with the value at I. And then you will again apply Heapify on the swap node. This is what you have to do. So we'll be writing a recursive algorithm because it will be more intuitive to write a recursive algorithm. So max Heapify. Keep in mind, if you want to do min Heapify, just apply minimum. Wherever we are doing maximum, do minimum. Wherever we are doing largest, take smallest. Okay, then it will be min Heapify. So max Heapify of what all should you have? An array. It is the array representation of the heap. Then I is the node on which you want to apply heap. Here we'll consider I as root. Then you have n, which is the size of the array. So what are the variables that we'll need here? Think of the variables we'll need. One is we have to keep track of the largest. So we'll have a variable largest. Largest will keep track of whatever is the largest element. Then we want to keep track of left child and the right child. So these are the three variables we'll need. So at the initial point, what we'll do, we'll assume that the largest value as of now is I. Whichever node is the root, that is the largest. This is what we are assuming for now. Then what is the left child? Left child will be 2i plus 1. And what about right child? Right child will be 2i plus 2. So you got the three variables, largest, left child and right child. What is the next thing that you want to do? You want to compare between these three and see whichever node has the maximum value. So 2i plus 1, 2i plus 2, these are indices. You want to go into that index, check the value of that node and see which among these three nodes have the largest value. So how will you check that? If condition. Under if condition, what should you have? First thing, you should check whether the left child exists or not. So it may be the case that you have already exhausted the whole heap. So how do you check whether left child will exist or not? Whatever is the left index, that should be lesser than n, because if n is the size of the heap, last index will be n minus 1. Your indices will be 0 to n minus 1. So your left index, whatever you calculated, that should be lesser than n. So if left is lesser than n, which means left child exists. And what is the second condition? You want to check whichever is the largest, left child or the value at root. So as of now, we already considered, we assume that largest is I. So this largest, we are storing the index I. Okay. So what will you do? AR of array of left is greater than AR of largest if. That is, if this is the case, then what should you do? That is, here it is saying left child is larger than whatever is presently the largest. That is, presently you are assuming I is the largest. If left child is larger, then you should update largest to left, because you know left child is the largest till this point. So you will update this variable largest to whatever is the index of the left child. Next thing, we have to check with right child. So if the same thing, right is less than n, why am I doing this? To make sure that the right child exists. And what is the second condition? My right child, if this is greater than AR of largest. If this is AR greater than AR of largest, what will I do? I'll update largest as right. So at this point, what I've done, I've already checked the root node with both the left and right. And as of now, the variable largest will be holding the index of whichever is the larger one. So if root is larger, this largest variable will be having the index of root. If left child is largest, then this largest variable will be having the index of left child. And if it is right child, then that. So as of now, whatever value I am having in the variable called largest, that is the maximum among these three nodes. So the next thing that I have to check, if whether this largest is root itself. So if it is root itself, I am done with heapify. But if it is not the root, that is when I again have to heapify. So if largest not equal to I. So if it is equal to I, there is nothing more to be done. This much is good enough. I'll stop the heapify. But if it is not equal to I, what do I have to do? I have to swap. So I'll write swap. What do I have to swap? I have to swap AR of I with AR of array of largest. So when I do this, what happens? The value at root gets swapped with whichever is the largest value. Okay. And once I swap, the next step is to apply the same max heapify algorithm on the swapped node. That is whatever is the child node to which I swapped. On that node, I have to again call max heapify. So what will I do? I'll again call max heapify on the same array. What instead of I, which I passed here, what should I pass now? I should pass largest, whatever is that index. And then I should have n as the size of array. So this is the max heapify recursive algorithm. So this will keep on recursively going through the tree the same way we saw in the practical case. It will go till the end and it will heapify the complete heap. So the next question is, what are the space and time complexities of this algorithm? So in order to understand time complexity, you want to see how many steps will it take at max. So at max, if you have something like this, what happens in Heapify? In Heapify, it doesn't go horizontally. It only goes vertically. Every time it is searching for both children, and it may swap. In case of a swap, it will move downwards. Every single loop of Heapify or every single step of Heapify, it will be moving downwards. So maximum number of steps that it will take to complete is same as the height of this tree. That is height of the heap. Okay. That is the maximum number of steps that we take to complete. So in binary tree lectures, whenever we had cases like this, we had time complexity as order of n. And what is the reason for that? The reason was that there could be a skewed tree. That is, tree can simply grow like this to one side. In that case, the height could be order of n. That is the reason why in binary tree lectures, whenever we had situation like this, we said time complexity is order of n. But because this is a heap, time complexity is order of log n. And do you know why it is log n? It is log n because the maximum height possible for a heap is log n. So in the lecture where we discussed about height and depth, we clearly went through all these calculations that the maximum height possible for a complete binary tree with n nodes is order of log n. So heap by definition is a complete binary tree. So because it is a complete binary tree, the maximum height of a heap is order of log n. So because of that, the time complexity of Heapify algorithm is order of log n. What about the space complexity? Because you are going for a recursive approach, you are calling this again and again. That is, max Heapify is called every time you are calling this algorithm. So at max, you can call it order of log n times. And in that case, your recursive stack can take up order of log n space. So in this recursive algorithm, space complexity is order of log n, time complexity is also order of log n. But if you want to decrease space complexity, you can use an iterative algorithm. So in the next lecture, we'll see the iterative Heapify algorithm, which will decrease the space complexity to order of 1. So instead of recursion, when we make use of iteration, you can take space complexity down to order of 1. So that we'll see in the next lecture.